Today we are discussing about the CAN. CAN is actually the controller area network. So that was invented by Bosch in 1980s, and before the introduction of this CAN controller area network, the devices, different networks in the car and automotives were connected by analog network, and it was difficult to trace these devices. So Bosch invented this, introduced the CAN in 1980s, and because of that invention, it was very easy to connect all these devices in the automotives. The the devices in the controller network or the device in an automotive is normally termed as a node. Normally a power steering can be termed as a node, airbag can be termed as a node, an air conditioner can be termed as a node, and here you can see that over 700 and over 70 nodes can be used in a vehicle, such as engine, power steering, anti-lock brakes. All these devices can be treated as nodes in the vehicle. So this is a node. This is a node. This can be a power steering. This can be a power window. Node 2 can be a power window, and this node 3 can be an airbag. And the advantage of CAN is it is very low cost and efficient. And we are using a CAN bus for communication. CAN bus is actually a twisted pair wire terminated by the two ends by 120 ohm resistor. Here we will use a 120 ohm resistor, and here also we will use a 120 ohm resistor for termination, and this is a twisted pair wire, that is actually the CAN bus. We can connect as many as 70 devices to a CAN bus. Each node has got an identifier. Each has got a normally 11-bit identifier will be used, and based on this identifier, the priority in accessing this bus will be decided by this identifier. So priority, we can, all the devices cannot simultaneously access the device. Only one device can access the bus at a time, and that is decided by the identifier. And the value identifier having a lesser value will have more priority for accessing the bus. If the value is higher, it will have lesser priority. So identifier having lesser value will get priority over identifier having higher value. And the another advantage of this CAN bus is it is highly reliable. Reliable means there will be an error detection and correction mechanism in the CAN bus. If there is an error if there is some electromagnetic interference in this bus, so what will happen is that will appear in the two wires simultaneously, and that will come as a common mode signal, and that will be cancelled. So there will be error cancellation mechanism will be there in the CAN bus. And again, this CAN bus is highly robust also. That is, even if the devices are situated at different coordinates of the vehicle, there can be a lot of electromagnetic interference can be possible, and because of that there will be errors may be there, and that errors can be reduced. That is, the electromagnetic interference can be reduced due to this error correction mechanism, and because of that common mode cancellation, we can reduce the errors. And again, we can use the CAN bus in extreme temperature conditions. Normally the bus will be situated inside your engine room, and sometimes it may be outside the vehicle, and in any condition it can be used. So that is the advantage of the CAN bus. It is highly robust also. And again, the fault tolerance mechanism is also used in the CAN bus. Fault tolerant means if there is some error, that correction mechanism also will be there in the case of a CAN bus. Again, the CAN bus is highly flexible also. CAN bus is flexible means if you want to add one more node, here one node is there, that is, suppose it is power steering, this is power window, this may be airbag. Suppose I want to introduce ABS also, I can very easily add the ABS to this CAN bus. So that is the advantage of this CAN bus. It is highly flexible also. You can see we are adding node 3 and node 4, node 4 and 5 with this CAN bus. Now we can see about the different features of this controller area network, the how CAN bus protocol functions, the operating principles of CAN bus, different message formats. Different message formats means we have to identify the device, so message formats are there. Then working with STM32, that is Texas Instruments CAN controller. This is a Texas Instruments CAN controller. This is controller area network protocol was originally developed during late 1980s by a German company, Robert Bosch, for the automotive industry. It was invented for automotive industry, but now it is used in medical field and as well as in almost all industrial applications, aviation field also, and it is a small master serial communication. It is a serial communication, not parallel communication. It is a multi-master serial communication bus whose basic design specification called for high speed, high noise immunity. That is high noise immunity because automotives work in highly noise environment and error detection features. Then CAN offers data communication up to 1 megabit per second. The error confinement and the error detection features make it more reliable in noise critical environments in the automotive industries. Normally the engine compartment will be highly noisy, that so many things are working, and the temperature is also very higher. So there will be a very good error detection correction mechanism is also there in the CAN bus. Now we can see the attractive features of the CAN. It is the basic the most attractive feature is it is very low cost, and it is highly robust, high data transmission speeds up to 1 megabits per second. Then reliability, excellent error handling and correction mechanism, automatic retransmission of faulty messages. That is, if there is a fault in the message, it will automatically retransmit. Then automatic bus disconnection of nodes that are suspected to be physically faulty. That is, if one device is found to be faulty, it will automatically disconnect that device from the CAN bus. Then functional addressing, that is, the data messages do not contain source or destination address, only identifiers relating to their function or priority. That is, this message that is sending to the CAN bus will not have any source or destination address, only identifiers relating to their function and priority. That is, each device will have some priority, and based on that it will assess the bus. And then this is a CAN bus, that is different nodes are, this is the CAN bus, this blue line is the CAN bus, and different nodes are connected to this CAN bus. This is termination that we have seen. We will terminate with by 120 ohm resistor. It is the characteristic impedance is 120 ohm, and again different here 5 nodes are there, and it is a broadcast type bus. Broadcast type bus means if node 1 is transmitting, it will transmit to all the devices in this bus. It may listen. If one bus if one node is transmitting, all other nodes can listen, and only the node corresponding to the required information only will receive that information. Other devices will simply listen the transmitted messages only. So that is how the communication is taking place. So it is a broadcast type message. That is, if it is similar to a radio broadcasting, If you want to receive, you can turn on your radio. It is transmitted everywhere. Similarly, here also it is a broadcast type bus. It is transmitting from one node. It may receive, if it is intended for this node, it will receive only in this node, but the other nodes also can receive. All devices can hear the transmission. All the devices can hear the transmission. No way to send data specifically to a node by its address or something. Suppose I want to send from here to here, I cannot directly send from here to send here. I can broadcast in this bus, but it can receive. These others can listen. All nodes will pick up the traffic on the bus. All nodes will pick up the traffic on the bus. That is, the traffic is decided by all the nodes. Then the CAN stand defines a communication network that links all the nodes connected to the bus and enables them to talk with one another. That is, that we have seen. If you have to send one thing, we have to transmit, we have to broadcast in the network. There may or may not have a central control node. That is, there can be a control node or there cannot be a central control node, and nodes may be added at any time. That is, if I want to add another node here, I can add while the network is operating. Even if it is working, I can add another node. That is, we can have hot plugging. Then the CAN's attractive feature is it is a broadcast type bus. That is, you might have seen a USB. USB is a point-to-point communication, Ethernet. All these things are a point-to-point communication, but CAN does not send data to a point-to-point format. That is, it is not sending data from node A to node B, but it is sending in terms of a broadcast type message. And now we can see what are the things that will be there in a CAN node. So normally a CAN node will have a microcontroller will be there. So this node means this can be a power steering. So in a power steering also there can be a microcontroller. Then a CAN controller will be there, and again a CAN transceiver will be there. And here there will be a data transmission, and here the data will be differential. From CAN transceiver, the data output will be a differential mode. That is, that can be this will be for 0. It will have in one bus one bus is known as CAN high bus, and the other bus is known as CAN low bus. So in high bus, if for 0 it will have +5, and for 0 it will have -5. For 1 both will have 0, like that. So this is the schematic of a single CAN node. So in one node there will be a microcontroller, there will be a CAN controller will be there for controlling this data to transceiver. So CAN transceiver is actually converting the data into a differential mode signal. So here you can see that node B, for the node B it will have a CAN controller, a CAN transceiver, and it is connected to the CAN bus, and it is terminated at the two end by 120 ohm resistor. And here another nodes are there, node A and then node B is also there. These two nodes are similar to node B, and this is connected to CAN high bus, and this is the output from the one output of the transceiver is connected to CAN high, and the other is connected to the CAN low. And here this is the electronic control unit. This can be this node, CAN node 1 may be the electronic control unit for power steering, and this may be the electronic control unit for power window, and this will be connected to the CAN bus high line and CAN bus low line, and this is connected with a terminating resistor of 120 ohm. The output of the CAN controller will be a digital signal, that is zeros and one, and this output of the CAN controller will have only zeros and one, and from that CAN controller we are using a CAN transceiver to convert that digital signal into so that can be connected to CAN high and CAN low bus. So when you are sending a logic 1 means both CAN bus will have equal voltages in the bus, that is, it can be 2.5 volt here. Both CAN high as well as CAN low will have 2.5 volt, and the difference is 0. So this is known as recessive mode. So when you are sending a logic 1 means both CAN high and CAN low will have 2.5 volt in the bus. So the difference between that voltage is 0. And when you are sending a logic 0, the CAN low will have 1.5 volt in the bus and CAN high will have 3.5 volt in the bus. So the difference is 2 volts. So for zero logic, the difference voltage is 2 volts between CAN high and CAN low, and that mode is known as dominant mode. Mode is known as dominant mode. Initially, we will for dominant means there will be a start of frame will be there in each message format. So start of frame will be we will use a 0 logic, so that we can have a dominant mode in that. And the recessive means that is a suppressed, like recessive means similar to a suppression. So recessive mode means logic 1 and the difference voltage between the CAN high and CAN low is 2 volts. Between CAN high and CAN low is 0 volts. This is the functional block diagram of a CAN transceiver. You can see here. So this is the D data input, and this is the data received. That is normally the data we are transmitting will be sent back to the microcontroller unit. That is at this point itself there is an error checking will be there. So this is the CAN high, this is the CAN low, and here suppose this is the microcontroller unit, the CAN transmitter, CAN TX, CAN RX. So here data, the digital data, we are converting that into if you are connecting here, if you are connecting 0 here, if the D is 0, you can see that if the D is 0, you can see that this is the logic 0. CAN high will have 3.5, and the CAN low will have 1.5, and the difference is difference voltage is 2 volts. And similarly, if it is 1 volt, both will have CAN high and CAN low will have 2.5 volts, and the difference is 0 volts, and the transmitted data will be feedback to the microcontroller unit. So that is for an error checking and correction mechanism we are using this. And this is one of the data sheet of CAN controller from Texas Instruments. Here you can see the bus voltage in the dominant mode and the bus voltage in the recessive mode. In the dominant mode, it will have CAN high will have VCC, and CAN low will have 1.25, and here it will have in the receive mode, CAN high and CAN low will have 2.3 voltage. So here the difference voltage is VCC minus 1.25. If the VCC is 3.3, approximately the voltage is 2 volt. If the VCC is 3.3, the difference is approximately 2 volts. In the recessive mode, you can see the recessive mode, CAN high, both CAN high and CAN low will have same voltage. So the difference is 0 volts. Now we can see what will happen if node A and node B are trying to access the CAN bus. If node A and node B, suppose at time t equal to t1, node A, this is T1, this instant is T1, this node A is in the dominant, that is dominant means 0, and B, node B is also in the dominant. So both are trying to send 0. So what will happen? The bus will be in the dominant mode. Suppose node A is sending a recessive and node B is sending dominant. So the bus will be in the dominant mode. Bus will be in the dominant mode. And here at another instant, suppose A is sending dominant and B is sending a recessive. A is sending dominant and B is sending recessive. So here it will be again dominant, that is 0 into 1 is always 0. So it is again dominant. Again this is recessive. Both are 0. Recessive means actually it was 1, but when we are recessive means here the value will be recessive means the value will be 0 for corresponding to 1. Both will be recessive in nature. Then now we can see about the CAN signaling. Signaling is differential, which is where CAN derives its robust immunity and fault tolerance. Differential means that we have seen CAN will have CAN high line and CAN low line. So for 0 we are sending, for digital 0 we are sending plus 3.5 and 1 plus 3.5 in CAN high and 1.5 in CAN low bus. So the difference voltage is 0. And again balanced differential signal reduces noise coupling and allows for high signal rates over twisted pair cable. That is we are using balanced signaling, we can reduce the noise effect in the twisted pair cable. Balanced means current flowing in each signal line is equal but in opposite direction, resulting in field cancelling. That is, as in the twisted pair cable, the current flowing in each line is in opposite direction. So there will be a noise cancellation effect will be there. Then the use of balanced differential receivers and twisted pair cabling enhance common mode rejection and have high noise immunity for a CAN bus. So we know common mode rejection ratio in the operation amplifier. Similarly, here also we can reduce the noise by using common mode rejection. And again there is a characteristic impedance of 120 ohm. That is why we are terminating the terminating the cable with a 120 ohm resistor. So similar to our coaxial cable will have a 75 ohm characteristic impedance. This CAN bus will have a 120 ohm characteristic impedance. Now we can see what will happen if one or two nodes, two or more nodes are trying to access our CAN bus from different modes, from different nodes. Suppose we are trying to access the CAN bus, and what will happen? The device having higher priority only will get the access. That is what is actually described here. The CAN communication protocol is a carrier sense multiple access protocol with collision detection. That is, if there is more than one device is trying to access, only one device will get the priority based on its priority. CSMA means carrier sense multiple access. Carrier sense multiple access means that each node on a bus must wait for a prescribed time period of inactivity before attempting to send a message. That is, if the bus is not getting in the first attempt, what will happen? It will wait for approximately 7 cycles. It will wait for approximately 7 cycles, and again it will try to access the bus. So again, if it is not getting the bus, again after 7 or 8 cycles, it will try to access the bus. So collisions are resolved through bitwise arbitration based on pre-programmed priority of each message in the identifier field of the message. So each device will have its own priority. So normally the first priority will be for the airbag. You might be knowing, if something is happening, airbag should work perfectly. So the priority of the device will be based on the safety needs. So brake, all these things have priority. Then higher priority identifier always wins the bus. Again, now we can see different three nodes are there. Node 1, it will have an address of 65D, and another node 2 will have an address of this is known as arbitration ID. It will have an address of 676, and the other is 659. So which is the lowest in this? 659 is the lowest. So 659 is the lowest. So this if these three nodes are trying to access the bus, this node will get the priority, and this node will get the access of the CAN bus. So we can see how it will happen in the next slide. And again, in each message format, there will be an 11-bit identifier is there. You can see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 11-bit identifier will be used. You can see this is the 11-bit identifier, that is 4-bit, 8-bit, 8 plus 3, 11-bit. So there will be an 11-bit identifier will be there, and before that there will be all the bus, there will be a starter frame. So starter frame is actually we are giving a 0 means this is the digital 0. So digital 0 means here CAN high will be plus 3.5, CAN low will be 2.5. So the difference voltage is 2 volts. CAN high will have plus 3.5, CAN low will have 1.5. So the difference voltage is 2.4. All the bus will have this. Even if all the nodes are trying to access, only one CAN bus is there. So CAN bus will have this voltage level. So that is actually what is happening. So this is the starter frame. SOF. Here you can see the starter frame. So all the nodes will send a 0 as the starter frame. So while sending the starter 0, the bus will have, CAN bus will have a plus 3.5 and a 1.5. So the difference is between CAN high and CAN low is 2 volts, and there is an 11-bit identifier is also there. Now you can see node 1, node 2, node 1, node 2 and node 3. Node 1, node 2, node 3 will have the first bit, the most significant bit will be 1. So here this is 1, this is 1, this is 1. So all these are 1 means this will be recessive, bus will be recessive. Here it was dominant, here it is recessive. Again check the second bit, again all these will have 1 1 1 1. So here this is digital value is 1 1 1, but again the bus is recessive. So in the second bit also the bus is recessive. Then look into the third bit. In all the bits, node 1, node 2 and node 3 all will have zeros. So this is zeros. So all these are 0 means the bus is dominant. Now check after up to 4 digit, up to 5 digit, all will have up to the 5th bit. All node 1, node 2 and node 3 will have same format, same digital format. So this will have same format. And the 6th bit, look into the 6th bit, node 2 only will have change. Node 2 will be 1, so it is a higher value. Node 2 is having a higher value than node 1 and node 2. So here node 2 will loses its priority. So node 2 will send 1, but node 1 and node 3 is sending zeros. Node 1 and node 3 is sending zeros. So the bus is dominant. So now onwards the node 2 is listen only. node 2 loses its control over the bus. Node 2 loses its control over the bus now onwards. And here in the fourth bit and the third bit, node 1 and node 2 will have same data format, that is both are recessive, both are sending recessive bits. So bus is recessive. So now we have to decide which node will get the priority. So you can see which will have lower value in this node 3 and node 1. Based on that node will get the access to the bus. Now check for here in this bit you can see, node 2 node 2 will node 2 already loses its access. Node 1 loses its access. Because it is sending a 1 data. So 1 data, here it is sending a 0 data. 0 means it is lower than 1, so it is sending 1 and this is sending a 0, and as you are sending 0, the bus will be dominant. From here onwards it will have listen only. This will be listen only. So from this point onwards, node 3 is the winner. Node 3 will get access to the bus. This is how the priority is decided between the different nodes, and based on that the bus will be chosen. The CAN bus will be chosen by the node, and now the node 3 has access to the CAN bus, and the CAN data will be sending by this node 3, and the others can listen to the bus.